Okay, here's a question for you. Why do sounds not last forever? For example, why do I not hear my voice just reverberating infinitely from the walls of the room I'm recording in right now? Go ahead and think of maybe why that would happen and just have it in your mind, I guess. It's not exactly obvious, like there's nothing in our everyday experience that would tell us that sounds should decay and die off. So, what's going on here? Like all physical phenomena, sounds are made possible through a transfer of energy from a source to the medium itself. Without that energy coming from a source, such as a voice or an instrument, the fluid medium could not actually oscillate and sustain what we perceive as sound. We know from experience that sounds eventually die off, like they don't just last forever. So that means they must be losing this energy somehow. But where does that happen? How does a sound just run out of energy? It's not exactly obvious there either once we have introduced the idea of energy into the whole idea. There's still questions. Where does that energy go? How is it transferred? What is it transferred to? Is it lost forever? Is it useful in any way? There's still a lot of questions to unpack there. Conservation of energy, probably the most well-tested law of physics, tells us that energy cannot be created or destroyed, it can only be transformed and transferred between objects. So somehow our sound wave as it dies out is doing one of those two things. It's transforming energy into some other form that's not useful for the sustaining of the sound, or it is giving that energy to some other body. The transfer and transformation of sound energy happens via two primary mechanisms, those being absorption and attenuation. Each type of energy transfer is differentiated by where it takes place. Absorption being energy transfer occurring at the boundaries of our medium, such as when the sound wave meets a wall or other physical object, and attenuation being the energy loss and transfer that happens as the wave is propagated within the medium itself. Both absorption and attenuation are absolutely critical factors in determining how a room will sound. Absorption is more relevant in smaller spaces where reflections will occur more frequently, such as in the home studio I am in now, or in a small like club or bar venue. Attenuation becomes more important in larger spaces where sound waves can travel unimpeded for relatively longer distances, such as large concert halls, movie theaters, arenas, or even just Earth's atmosphere itself. This video is going to build on some concepts I outlined in the previous episode of Scitone that was covering reflections. So if you'd like to have a better understanding of what we're about to go through, you might want to watch that video first, but you can still get some very valuable information either way. Alright, let's dive in. Like I mentioned, in part 1 of this series, I discussed reflections, which is only part of the whole story of what happens when sound meets a boundary. Absorption tells the rest of that story. When a sound encounters a physical boundary like a wall, only part of the sound's energy will be reflected into a new sound wave. The rest of it will either be transferred through the wall, intact but modulated, or it will be absorbed by the boundary itself. So we lose the energy from our reflection that is either absorbed or transmitted through the boundary. How does that absorption take place? Friction is ultimately responsible for our loss of energy here through absorption. When air particles near a boundary are excited by an incoming sound wave, some of them are going to move towards that boundary. The particles that are not immediately reflected will move into the boundary's interior until they eventually collide with something. When that collision happens, those particles are going to transfer all or part of their energy to the interior of the boundary itself. That piece of the interior is then going to be set in motion from its newly gained energy. But because it's part of a solid object, that material is going to experience a lot of friction as it starts moving, meaning the energy it gains from the air particle will be quickly dissipated as heat. This is how sound energy is lost to a boundary such as a wall or other absorbing material. Particles sustaining the sound wave are allowed to move into the boundary's interior, ultimately transferring their energy to some piece of the interior when they collide with it. When that material moves after it gains energy from the incident air particle, it will quickly experience heavy frictional forces and dissipate its energy as a very small amount of heat. In light of this, we see that a material's porosity plays a very significant role in its ability to absorb sound energy. A perfectly impermeable material could not demonstrate this type of action because particles can't move into its interior and can't make their energy go anywhere other than a reflection or or transmission. In general, better airflow through a material will mean a better ability to absorb and transform sound energy. If more air can flow through a material, more particles can be trapped on its interior, and thus their energy can be more efficiently transferred into heat. However, if the material is too loosely packed, the friction required for this transformation will not be strong enough to make the material an efficient absorber. So there's a balance of density along with a required level of porosity that we need for a material to be a good absorber. This type of sound absorption I've just described does not happen uniformly for all frequencies of incoming sound. In general, higher frequencies will be more efficiently absorbed by this mechanism of a material's porosity. This happens due to the velocity dependence of a frictional force. The magnitude of any frictional force is directly dependent on the velocity of the moving object. By definition, a high-frequency sound is going to complete more oscillations per unit of time than a low-frequency sound. A high-frequency sound setting an absorbing material into motion is going to cause that material to move faster than it would if a low-frequency sound were causing the same effect, meaning that the frictional force experienced by that material will be greater for the higher frequency case, which ultimately means more energy from that sound wave will be transformed into heat energy for the higher frequency case than would be for a low frequency case. Think of the heat generated when you rub your hands together to understand this concept. If you rub your hands very quickly, then you'll generate a good bit of heat. However, if you rub them slowly, you probably won't experience any heat beyond the heat your hands already have. Even if you expend the same amount of energy during the motion, say moving your hands very quickly for 1 second or moving your hands very slowly for 10 seconds, even if you expend the same amount of energy, you're always going to generate more heat when you move faster. Another reason low-frequency sounds are not absorbed efficiently by materials in the fashion I've been describing is due to the size of the materials. To efficiently absorb sound energy, the material needs to have a thickness comparable to the wavelength of the sound it is absorbing. For example, a sound wave at 100 Hz has a wavelength of around 11 feet, which is not really practical for a thickness of a wall-mounted absorber. I mean, that might be wider than the room itself. So we know that porous materials are excellent absorbers of sound for mid and high range frequencies. What types of materials are commonly used for this purpose? The most common absorbing material we've probably all encountered is a carpeted floor. Carpet is obviously very porous, meaning that sound energy can move particles into its interior very effectively, and that material can then dissipate their energy as heat because the particles are allowed to move into the interior. However, we can't forget that absorption is frequency dependent. Carpet will do very little to absorb low frequency sound, in part due to its thickness. So carpeted rooms will often have a very unbalanced reflection picture due to the abundance of low frequencies that are left unchanged by the carpet. Drapes are also porous materials that make good absorbers for high and mid frequency sounds. Heavier drapes will provide more efficient sound absorption due to their increased density, which ultimately means more friction as fibers are packed closer together, and as they move from incident sound energy, there's more friction available to actually move that energy away as heat. The degree of folding will also have a significant effect on sound absorption for a drape. Imagine if the drape is folded just in a single plane, sound energy is going to move into that boundary once, right? But let's say it's folded here and then folded back on itself again. Sound wave comes through, is absorbed by the first part, energy that is not absorbed then hits the second fold. So if you fold something like that many times, you're basically getting free absorption for the same amount of material. Fiberglass boards and tiles also make very good absorbers due to their level of porosity and their low profile design. There are thousands of varieties of these types of panels available for purchase online. Really, the details of what you might need will depend on the geometry of your space and what kind of things you record in that space. Acoustic foams are also a relatively inexpensive way to increase the sound absorption of your space. They're very lightweight, easy to hang, relatively inexpensive, and they're very porous, meaning they will help you absorb some high and mid frequency sounds. A lot of producers and engineers will place foam like this in very critical regions of their room, such as behind their speakers and spots where first reflections are likely to occur. So far, we've discussed sound absorption made possible by a material's porosity, letting air particles in and trapping their energy and converting it as heat. But we know that that is not very effective for low frequency sounds. So, what methods are available to reduce the energy of those low frequencies? A very common approach to this problem is to use what's known as a panel or diaphragmatic absorber, generally constructed with a panel of some material held maybe a few inches away from a wall by some other supporting edges. Basically, like a box with an open face, where the open face would be against the wall. Absorbers like this take advantage of a physical principle known as resonance, or more specifically mechanical resonance, to reduce the energy of low frequency reflections. How does this happen? First, we need a better understanding of what mechanical resonance actually is. And to do that, we need to understand something called mechanical impedance. Mechanical impedance is a general quantity defining how efficiently a system or object can be moved in result to a disturbing force. It is a ratio of force applied to resulting velocity. Mathematically, this quantity is composed of a mechanical resistance term, which encapsulates the details of dissipative forces on the system, and a mechanical reactance term. Depending on the mass of the oscillating body, the stiffness of the medium, and the frequency of the driving force. Mechanical resistance is determined entirely by the details of the system itself. For example, sandpaper moving across a surface will experience more friction than a piece of printer paper moving across that same surface. We might encapsulate this difference in a mechanical resistance term that is really just created by the details of the system, not anything that we did to alter it. Reactance, however, is determined by the system's details as well as our driving force, so we have some level of control over how much it contributes to the overall mechanical impedance of the system. Okay, so now that we know what mechanical impedance is, we can actually discuss mechanical resonance. We achieve mechanical resonance when the frequency of our driving force takes a value that completely eliminates the reactive term from the mechanical impedance, meaning the only resistance to the system's motion comes from the physical details of the environment and the system itself. A familiar example of a system displaying mechanical resonance is a person swinging on a swing set. So imagine yourself swinging on a swing, right? The driving force that you apply is the kick back and forth of your legs as you swing. If the frequency of your kicks matches the natural frequency of the swing itself, you will be able to move the swing higher and higher on each arc. I'm sure you've done this at some point, as a kid maybe, or maybe more recently, who knows. But if you time your kicks correctly, you can apply force at an opportune moment, which will give you the most resulting velocity. Conversely, if you just start kicking back and forth really quickly, as the swing is already moving in its natural motion, your force is only going to act to stop the swing. You're not actually going to add any velocity to the system, even though you are expending energy. The same will happen if you start to kick your legs too slowly. The motion of the swing will die out over time because you aren't driving it at a frequency near its resonance, meaning the force you apply is not efficiently translated into actual velocity. Essentially, when you drive a system at a frequency near its resonant frequency, your force is mostly in phase with the natural motion of the system itself, which means that the force you apply is going to result in actual velocity much more efficiently than if your force were out of phase with the system's natural motion. If the concept of phase doesn't make a lot of sense here, check out Scitone episode 1, which is completely dedicated to the concept of phase and what it means. Okay, so now we understand mechanical resonance. Physical systems that are capable of oscillation all have a resonant frequency that basically means they can be operated more efficiently by forces applied near that frequency. We can take advantage of this mechanical resonance to absorb low-frequency sounds by constructing our panel systems such that they have a resonant frequency in our desired low range. So in this example, the panel on the front of the absorber is analogous to the person in the swing, and the distance of the panel from the underlying wall is analogous to the length of the swing's chain, or really how much leverage do we get, or how much mechanical advantage do we obtain. The mass of the panel itself, along with its density, and the distance of the panel from the wall are going to control what frequency our panel is resonant at. So let's imagine we have a panel absorber like this that is resonant at 200 Hz. Sound waves far from this frequency are not going to do anything to move the front of the panel because they're driving it far away from resonance. So, for example, a 4,000 hertz wave is not really going to affect the motion of the panel at all because that's very far away from its resonant frequency of 200 hertz. However, sounds that are closer to the resonant frequency of 200 hertz can actually set the panel into motion, as we saw with the case of the swing set. So the sounds that actually do set the panel into motion are going to have their energy dissipated via the same friction mechanism that we were discussing with the porous absorbers, except now we've selectively tuned the panel and cavity system to operate at a specific frequency. The frequency can really be anything, but this is most commonly used for low frequencies because porous absorbers are already so efficient for mid and high frequencies. The absorption of this type of diaphragmatic absorber can be improved by filling the cavity between the panel and the wall with some kind of material, maybe like a foam or something like that, because that's only going to increase the friction that the panel experiences when it's able to be moved by that resonant sound. Absorption, like we've just discussed, for porous materials and for resonant absorbers is very important for smaller spaces where reflections will happen more often and our sound is going to encounter a lot of boundaries. But it's not the only way that sound waves lose energy. We also need to discuss attenuation, which happens as a sound wave travels through the medium itself. So we know attenuation describes the loss of sound energy as a wave is propagated. Think of a soccer ball being kicked on like a flat grass field. As the ball rolls, it's going to slow down just from encountering its environment, right? It's going to lose energy as it travels. A similar thing happens to a sound wave as it's propagated through a fluid medium. Because attenuation happens in the medium itself, it's much more important and relevant for larger spaces. In larger spaces like arenas, concert halls, and movie theaters, sound waves will encounter boundaries much less often, meaning that their energy loss as they travel needs to be considered more and more as the size of the space grows. So this attenuation of sound energy as it propagates happens in three primary ways: losses of energy due to molecular interactions, heat conduction, and viscosity. Fundamentally, sound waves move air particles, and those particles are going to interact with each other as they move, maybe colliding or maybe interacting via other mechanisms. In the case of a molecular collision, not all of the kinetic energy of those particles is going to be translated into resulting velocity, due to the particle's construction and internal nature. Some of that energy is going to be stored as a potential energy from a rearrangement of molecules in the vicinity of the collision. When groups of particles are rearranged like this, the potential energy of their combined system is altered, whether that is an electrical potential, gravitational potential, or thermal potential. It's going to be changed when their spatial orientation shifts. So when a collision causes that reorientation, some of that energy that would just be kinetic energy for the case of two lone particles is going to be spent on the rearrangement of that potential instead of just purely in the motion of the particles. Another way this energy can be transformed is from the internals of the molecules themselves if they are polyatomic. When molecules collide and interact, their motion is not always translational, meaning being measured from a reference point, kind of like the soccer ball. That would be a translational motion. Some of that motion will happen internally. The molecules may rotate, or the bonds between them, in like a diatomic oxygen molecule, let's say, the two oxygen molecules participating in that, instead of just moving from that collision, they might vibrate, or they might rotate, or they might do some combination of all three. But all of those require energy, right? So some of that energy is going to be spent on those other two modes of motion, being rotational and vibrational. The final way this energy could be spent is on an energy of association between ions in the fluid. Molecules and atoms interact via electromagnetic forces, primarily. The details of these electromagnetic fields are largely determined by the spatial arrangement of the particles contributing to the field. As sound energy acts on these particles, they not only need to overcome the forces of collisions, they also need to overcome the electromagnetic forces imposed on them by the environment. So some of our energy from the sound wave will have to be spent to overcome that, if the sound is to continue oscillating. So those three types of energy loss cover molecular interactions. Viscous attenuation happens whenever there is relative motion between districts or sections of our fluid, such as when a sound wave acts to compress a group of air particles or when it acts to expand them. Viscosity is a quantity basically describing a fluid's resistance to motion, almost like an impedance, but for the fluid itself. Basically, it describes if I apply force to the fluid, how much resulting velocity do I get from that? So you can think of this like peanut butter is much more viscous than water, right? Because if I just move water, it will move very quickly in response to my force and it will stay moving. But a jar of peanut butter, you can just get something stuck in it, right? Like if you move it, it's not just going to keep moving. The fluid or the whole system is much more resistant to motion than the case of water. All fluids have some degree of viscosity, so sound energy is going to be lost overcoming that viscosity no matter what the fluid is, even if it's just room temperature air, or water is a much better example. Sound doesn't travel as far through water, specifically high frequencies, due to its viscosity. The final type of attenuation loss is due to heat conduction, which is not really significant in small spaces or spaces that are temperature controlled. This is something that's more important on very large scales, such as sound moving across the surface of the earth. But nevertheless, it's caused by a bulk transfer of thermal energy that's happening kind of enveloping the system before the sound is considered. So we can imagine a current of air that moves from a higher temperature zone to a lower temperature zone, right? There's a bulk transfer of thermal energy going on there. So if I try to excite that space of air with a sound wave, my sound wave is going to lose some of its energy by being caught up in that bulk thermal process. It would not lose that energy if the temperatures were equal. If there was no bulk transfer of energy, I would just have to worry about the other types of attenuation. But since we're working on a large scale like this, maybe outdoors, if you try to excite that space of air with a sound, you're going to have to compete with that thermal conduction process. So now we know not only why sounds don't last forever, we have a conceptual understanding of what makes that happen. Maybe your answer at the beginning of the video was closer to the truth than you might have guessed. But either way, now we know. Sound energy is absorbed in some degree by any real-world boundary and is then transformed into heat due to internal friction. Sound energy is absorbed in some degree by any real-world boundary and is converted into heat through frictional forces. Porous materials serve as excellent absorbers of mid and high frequency sounds, whereas our resonant absorbers are more effective in the case of low frequencies. The molecular nature of fluids causes our sound wave to attenuate as it travels via the interactions of molecules from a molecular level, a viscous level, and a heat conduction level. But across all of these mechanisms, what ultimately happens is our sound energy is going to be converted into heat via some sort of friction or other molecular interaction. You might ask, could we use that heat somehow? Is there any way that it could be harnessed and used for a practical purpose of some kind? Maybe, but it will be very, very tough to do so. To brew a cup of tea, or basically bring water to a boil, you would need to capture, store, and timely apply the energy of millions and millions of people talking simultaneously. So maybe one day we'll have some technology that can actually make use of this heat that we dissipate from sound energy, but not looking likely anytime soon. All right, thank you for nerding out with me today. That's going to do it for Scitone. It was episode 3 now. Yeah, episode 3. Episode 2 of the Room Acoustics series. I love doing these videos. As you can tell, I'm a huge nerd. So yeah, thank you for checking out the video today. I really hope you enjoyed it, and I hope you learned a little bit about sound absorption and attenuation. The next part of this series is going to cover something really cool, diffusion of sound, which is a topic that I think a lot of artists and producers are kind of confused about. So I'm excited to get into that one. If you enjoyed this video, hit the like button, subscribe to my channel. I've got a lot more science content coming, got a lot more music coming, you know, all the good things, they'll be coming to the channel. So yeah, subscribe, and I will see you in the next video. Peace.